everyone, I'm Professor Harrison, and welcome to our module on matrix algebra for finance. In this video, we're going to be covering what a matrix actually is. We'll go through the basic definition, the notation we use to refer to matrices and their entries, and the most important name types of matrices that show up everywhere in finance. Throughout this module, we're going to be following a character named Ruth. Ruth is a PhD student in the early 1970s. She is developing a methodology for portfolio construction that uses matrix algebra in a way that nobody else is doing yet. The framework is hers, the math is hers, and her dissertation is going to be the formal write-up of all of it. Also in her PhD program is a man named Victor Callaway. They're both friends and they study together a lot, with Ruth explaining her work to him as she develops it. Today, Ruth has been working on the foundational chapter of her dissertation. The methodology she is developing relies on being able to talk about a portfolio of many assets at once. Before any of the optimization work can happen, she needs the language for the objects involved. That language is matrix algebra, and the chapter she is writing now defines exactly what those objects are and how they work together. She sits down at her typewriter to get started. A matrix is a rectangular array of numbers. That's the whole definition. It's just a table of values organized into rows and columns. The size of a matrix is described by two numbers, the number of rows and the number of columns. We say a matrix is m by n if it has m rows and n columns. The dimensions are just the shape of the table. So a 4 by 3 matrix has 4 rows and 3 columns, a 2 by 2 matrix has 2 of each, and so on. Each individual number inside the matrix is called an entry. The entry in row I and column j is written A sub ij. Under conventional notation, the first index is always the row, and the second is always the column. So A sub 2, 3 would be the entry sitting in row 2, column 3. Two matrices are equal if and only if they have the same dimensions and every single entry matches, the same shape and the same number in every single position. If even one position is different, then the matrices are not considered equal. So why are matrices useful? Let's apply them to an example where we have three stocks. We'll call them stock A, B, and C. We want to be able to talk about how a portfolio holds all three of these stocks at once. Let's say we wanted to talk about the returns of these three stocks over the last T months. If we wanted to do so, we need some way to actually represent what those returns are doing in each of the months. One easy way to represent this is with a matrix. We can organize the data so that the months are rows and the stocks are the columns. The entry in row 2, column 1, for example, is going to be the return on stock A in the second month. The entry in row 5, column 3 is going to be the return on stock C in month 5. The whole table is just a matrix with T rows and 3 columns. We use a capital R to denote it in finance. This matrix R is what we call a rectangular matrix. Rectangular just means that the number of rows is not equal to the number of columns. So for example, if T is 50 months, then R is going to be 50 by 3, a rectangular matrix with 50 rows and 3 columns. And by putting things into this matrix form, we have an easy way to look up any of the returns that we want for either of our three assets. Matrices can also be used to represent other things in finance besides returns. For example, let's say we wanted to investigate the covariances of our three assets. If we wanted to do that, we could calculate all the covariances separately, or we can end up representing them through a matrix. This matrix will be called the covariance matrix, and it's going to have the covariances between each of the asset pairs represented in a square. So, for example, with three stocks, there are pairwise covariances among each of them, and we organize each of the stocks so that each one has a row label and a column label. We get a 3 by 3 matrix, and we can use the capital Greek letter sigma to denote it. Sigma is what we're going to call a square matrix. Square just means that the number of rows equals the number of columns. So for example, here we have a 3 by 3, the same on both sides. So how exactly does a square matrix work? Well, one interesting set of entries is the diagonals of sigma. Here the diagonal entries are going to be the entries where the row and column number are the same. So for example, row 1 column 1, row 2 column 2, and row 3 column 3. Those entries are not actually going to be covariances between two different stocks. They instead are going to be the covariance of each stock with itself, which is just the variance. So the diagonal of the covariance matrix is the variances of each of our assets. Then the off-diagonal entries are going to be the covariances between the different pairs of stocks. So for example, if we wanted to figure out what the covariance is between asset A and asset B, we could look in the first row and the second column to find that covariance. There's another important property here. The covariance of stock A with stock B is going to be the same number as the covariance of stock B with stock A. They're both measuring the same thing, so the entry in row 1 column 2 equals the entry in row 2 column 1. More generally, A sub ij equals A sub ji for every pair. When that property holds, we call the matrix symmetric, meaning the off-diagonal entries all reflect one another on the other side. One nice thing about square matrices is we can basically represent any type of covariance relationship. For example, if we have three assets that are completely unrelated to one another, then we're going to have 0 in all the off-diagonal entries of sigma. In that case, only the diagonal entries are going to remain, and you're going to end up with what's called a diagonal matrix. A diagonal matrix is a square matrix where every off-diagonal entry is 0. In our setting, a diagonal covariance matrix would describe a world where the three stocks are completely uncorrelated. There's two other name structures that may appear within the world of finance. These examples are not symmetric matrices. First, if you took only the entries on or above the diagonal of sigma and zeroed out everything below the diagonal, you'd have what we call an upper triangular matrix. If you took only the entries on or below the diagonal instead, that would be a lower triangular matrix. Triangular matrices come up later in the module when we start solving systems, but for now, we'll just name them as the shapes and we can recognize them when they come up. There's also one more object that we need for our notation, the portfolio itself. A portfolio of three stocks is described by how much of each stock you hold. So the portfolio is just three numbers. We're going to organize them as a single column with 3 rows and 1 column, with the 3 rows representing the amount that we hold in each of the stocks. We're going to call the column W lowercase, which is going to be our weight vector. This is a 3x1 matrix, and a matrix with only one column is often called a column vector. If you took the same 3 numbers and laid them out in a single row instead, that would be a 1x3 matrix. A matrix with only one row is called a row vector. Both of these are perfectly valid ways of representing the exact same thing, and the difference here is just whether you use the rows or the columns to signify the 3 different stocks. If we want to talk about how these 2 different methods are related to one another, we would say that our column vector is just the row vector transposed. The transpose basically just means you're switching which are the rows and which are the columns, and we write the transpose of W as W prime. Finally, there are 2 other types of matrices that will often show up within the world of finance. The first is the identity matrix. The identity matrix is a square matrix that has 1s on the diagonal and 0s everywhere else. We write it I sub n for the n by n identity matrix. For example, the 3x3 identity matrix has 1s at row 1, column 1, row 2, column 2, and row 3, column 3, but everything else is 0. So why is this matrix important? Well, we're basically going to find that this identity matrix plays the role of the number 1 within matrix algebra, and we'll see exactly how that ends up formally working when we get to matrix multiplication. The second matrix that's important is the 0 matrix. The 0 matrix is the matrix where every entry is 0. It plays the role of the number 0 in the world of matrix algebra. In our setting, the 0 weights vector would just be 3 zeros stacked in a column, and it would describe a portfolio that holds none of the 3 assets. Ruth puts down her typewriter. She's now finished the notation chapter of her dissertation. By defining how matrix algebra works, she's set herself up to do more complicated things later on. So every optimization result, every covariance argument, and every portfolio statement she has is going to be written using this language. Victor stops by while she's working. They're in the same PhD program and they're becoming good friends. They've been studying together a lot lately, and when he sees the notation chapter is finished, he asks if he can borrow a copy for his own coursework. She lends it to him without thinking twice. So that is what a matrix is. A rectangular array of numbers indexed by row and columns, and we can compare them entry by entry. We covered the name types: rectangular, square, symmetric, diagonal, upper and lower triangular, column vectors and row vectors, identity, and 0. Every one of those names just describes the shape that the array takes. These name structures are going to be critical for figuring out things and having language to describe what's going on for the rest of this module.